Hello students, this is my first video on ICSE physics. So to start with the series of videos, first topic that we are going to cover in this particular video is moment of force or torque. So students, we are already familiar with translational motion. You already know what is translational motion. Whenever a force acts on a body and the body moves to a distance, then we say the motion is basically a translatory motion. So by the application of forces, we can produce translatory motion. Motion in a straight line or even motion on a curve is an example of translatory motion. But when we talk about torque or turning forces, torque is nothing but it is also a type of force that acts to turn a body. So turning effect produced on a body is only due to a torque. So as I said, in this particular topic we are going to discuss about moment of force of door. Knowingly or unknowingly, you are actually applying a torque. So when you are applying force on the handle of the door, you are actually applying a torque. So what is that? So when I am applying force on the door, it is acting at some distance from the hinge of the door. So this force is acting at some distance from the axis of rotation of the door, which is nothing but the hinge. So this particular product of force and the distance from the point of application of force and the hinge of the door is nothing but it is called torque. So with few examples we can understand these. So if you check out these diagrams, you understand that the torque is nothing but a force which is acting. So a torque is nothing but it is a force acting at some distance from the point of axis of rotation. So that axis of rotation is nothing but it is a fixed end about which the turning will take place. So we can say that torque is nothing but turning effect. Students, take the example of a fan. A fan is rotation of a fan is an example where turning forces are acting. So here moment of force or torque. So students, torque is equal to force into perpendicular distance. So here this perpendicular distance is nothing but the distance from the axis of rotation and the point where you are applying the force. Here from this particular figure, if you see, you'll understand that there are two forces acting from the axis of rotation. Say this is your axis of rotation. This distance is L by 2. So the force acting here is F1 and similarly here the force acting is F2. So here there are two torques which are being produced. One torque is, say, τ1 equals to F1 into L by 2 and similarly τ2 equal to F2 into L by 2. So there are two torques which are acting in this particular system. Now if the magnitude of the forces, that is F1 and F2, are equal, in that case the entire system will be in equilibrium. Suppose we are applying F1 equal to 20 Newton and similarly F2 equal to 20 Newton. So in that case, of course, there will be no turning effect since the total magnitude of force is same and distance from the axis of rotation is also same. So in that case, of course, we will not have any torque. The system will be in equilibrium. Now in order to turn this particular system, we need to apply torque. Two torques whose line of action are different and whose magnitude are also different. So that particular system will be known as a couple. Now in a couple, you can write down couple, we can say two torques acting together whose line of action are different. This constitutes a couple. Couple can rotate a body. So when two torques are acting together, they have the ability to rotate the body, but a single torque can only turn a body. It is a turning effect that can be produced by a torque. Now students, let us try to understand what are the conditions of equilibrium for a system of body. Now students, let us try to understand what are the conditions of equilibrium for a body. So here, first case is translatory equilibrium. In this case, the summation of all the forces acting on a body should be equal to 0. Second is rotational equilibrium. So in case of rotational equilibrium, the summation of all moments acting on a body or a system of body should be equal to 0. That is, summation of all the moments acting on the body should be equal to 0. Now if I say that a body or a system of particle is following both translatory as well as rotational equilibrium, then in that case we can say the system is in complete equilibrium. This means the body is neither moving on a straight line or curved path, nor it is having any kind of rotational motion. So we can say the body is in complete equilibrium. Remember students, if I am saying that the body is in only translatory equilibrium, this means I am giving an opportunity to the body to rotate. Similarly, if I say the body is in only rotational equilibrium, this means the body may undergo any kind of translatory motion. So when we say a system of particle or a body is in complete equilibrium, then it must follow both the system to be in translatory equilibrium as well as rotational equilibrium. So students, sum of all clockwise movement equal to sum of all anti-clockwise movement. So students, let us try to understand the principle of movement by this particular diagram. Here, as you can see, there are four forces acting, F1 and F2, and here are two forces, F1 prime and F2 prime. Let this entire length is L. From here, this length is L by 2, and this length is also half. This means half of L by 2, so it becomes L by 4. Now as you can see in the diagram, this particular moment is anti-clockwise movement and this particular moment is clockwise movement. Why this is anti-clockwise movement? Because it has a tendency to turn this particular system in anti-clockwise direction, and similarly these forces like F2 and F1 are students, all calculations should be done about the point where movement is taking place. So make sure that when you calculate the distance etc. while solving the problem from the diagram, you must ensure that all the calculations are done about the point where movement is taking place. Second point I would like to stress is locate the center of the system. So where is the center of your system? For example, if your scale is 1 meter, that is 100 centimeter, the center is 50 centimeter. So locate the center of the system while drawing the diagram. And third point is follow the principle of movement, that is all anti-clockwise movement should be equal to all clockwise movement. So following some of these important points, we are now in a position to solve some numericals in. So the problem is a uniform meter scale is kept in equilibrium when supported at the 60 centimeter mark and a mass capital M is suspended from the 90 centimeter mark as shown in figure. State with reasons whether the weight of the scale is greater than, less than or equal to weight of the mass capital M. So in this question we have to find out what is the weight of the scale. So here we are using the principle of moment. Now since we want to find out weight of mass capital M, and we have to see the relationship between capital mass of the scale and the mass suspended. So let us draw a figure here. Here small m is the mass of the scale and the distance of the fulcrum is 60 centimeter and the distance of the mass capital M is 90 centimeter. So here the fulcrum, remember, is at a distance of 60 centimeter. It is the point about which movement will take place, and the center of the scale, as we can see, 50 centimeter, and this is going to produce anti-clockwise movement, and this is going to produce clockwise movement. The capital M will produce clockwise movement, and the center of the mass or scale will produce anti-clockwise movement. So according to the principle of movement, clockwise movement is equal to anti-clockwise movement. So this is 50 centimeter from the center, one end of the scale from the center of the scale. Remember, that is the fulcrum, which is at 30 centimeter from the mass capital M, because capital mass M is at 90 centimeter and the fulcrum is at 60 centimeter. So 90 minus 60 is 30 centimeter. So we are using anti-clockwise movement, that is mass small m of the scale into 10 centimeter. We are taking 10 centimeter because see the fulcrum, distance of fulcrum there, it is 10 centimeter, and similarly capital M into 30. So here we are getting M equal to 3M. So mass of the scale is basically thrice of the mass of the weight suspended. So we have used the principle of movement to solve this particular problem. Thank you.